In this video, we will define an important subset of linear systems, and these are called homogeneous linear systems. And they play an important role in many important applications and even some other more theoretical consequences of linear systems. So in this video, we'll define what a homogeneous linear system is, and then talk about just a few basic properties. So what does it mean for a system to be homogeneous? Now we have essentially two ways of representing a linear system. We have the standard way, and in fact, let me go ahead and write the standard way down. So we have the a11x1 plus a12x2 plus dot dot dot, and then plus a1nxn. And then I know I have something over here, and then this pattern continues like this: a21x1 plus a22x2 plus dot dot plus a2nxn, and then again something over here, and then this continues until we have our m equations, right? So this is our standard m by n system: m equations, n unknowns, and it's a little incomplete now because I haven't filled in what goes on the right hand side. In fact, it is it's what happens on the right hand side that distinguishes a homogeneous linear system, right? So when we defined our linear system first, we had that all the a's could be real numbers, any real numbers, and then the b's could be any real numbers. Now, in a homogeneous linear system, all the b's have to be 0, right? And that's what makes the system homogeneous. So the left-hand side looks exactly the same as we've done several times now. It's the fact that all the b's here, that's what makes the system homogeneous, right? So right away, if you kind of think about it in terms of what has been our main goal, solving these linear systems. Well, if all the constants on the right hand side are 0, then right away we should be able to observe of an obvious, or often referred to as a trivial solution. Note x1 equals x2 equals dot 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 equals xn equals 0. In other words, if I replace all my variables on the left hand side with the number 0, then I would have found a set of values for my variables that would satisfy all m equations, because this whole expression here would be 0, and clearly 0 is equal to 0. So note that this solution set where all the variables are equal to 0, often called the trivial solution or obvious solution, right? So this always satisfies a homogeneous system. A homogeneous linear system, right? So what this means is, so therefore, homogeneous linear systems, they always have at least one solution. They have this solution. The question is, do they have infinitely many? Remember, a linear system can either have no solution, a unique solution, or infinitely many solutions. So the fact that we have the trivial solution for a homogeneous system, it means that a homogeneous system is always consistent. So hence, and this is an important fact, homogeneous systems are always consistent. They will always have at least one solution. Remember, consistent means at least one. Inconsistent means none in terms of solutions, right? Um, so so that's what it looks like in the standard form. Well, what about the um, if we express the system in augmented form? Well, it looks pretty much the same. So again, I'll do this a little abbreviated. So you'll have your A1, A2, no, A11, A12, A1N, and then A21, A22, A2N, dot dot dot, AM1, AM2, dot dot, AMN, and then now I would have my zeros there, right? So that again, this is a homogeneous system. So let's take a look at a specific example, and we will use something like we could go ahead and use our Gauss-Jordan algorithm to figure out what the solution is, right? So let's do an example. Right, so solve the following. Right, and let's do one where we have 3 variables, but just 2 equations. So basically like this, and let's say 2x1 plus x2 plus 3 x3 equals 0, right? So the fact that once we've written our linear system in the standard form, all the constants on the right hand side, since they're in this case both equal to 0, then we know this is a homogeneous system. And we know for homogeneous systems that we have at least one solution, right? So we have at least one solution, and the question is, do we have more, right? So is it only the trivial solution that satisfies this system, or can we find more? Well, let's write it in our augmented form. That way we can be a little bit more efficient when we do our whichever of our eliminations. I think we'll go ahead and do the Gauss-Jordan, get more practice with our reduced row echelon form. But there's the augmented form. We have our pivot right here, right? So we have our pivot. So the first thing that I like to do is, once I have my pivot in the upper left corner, eliminate everything below. Well, there's only one entry below. So all I have to do is take -2 times row 1 and add it to row 2, and that produces this other system where the first row stays the same. Then now I would have eliminated the 2 in the second row, so that's 0, and then a -2 times -1, that's a +2 plus 1, so that's 3, and then a -6 plus 3, that's -3. And then what's nice about having zeros here is that, again, doing any of our 3 elementary row operations will never change these zeros. So it's almost like you have a few less entries where you really have to keep track in terms of the arithmetic, right? This is not in any of our echelon forms because our leading coefficient here is not 1. So let's do 1/3 times row 2. Maybe I can squeeze it right here. So 1/3 times row 2. That produces 1, -1, 3, 0. Again, no change in the first row. And then 0, 1, -1, 0. Right? This is now, if you want to classify it in terms of our echelon form, this augmented system is now in REF, right? All our leading terms, all our pivots are 1, and in every and the pivots, they go down to the right, and every column that has a pivot has zeros below it, right? Now, to make it RREF, we have to make sure not only the entries below a pivot are 0, but the ones above as well. So I need to eliminate this. So what I can do is take row 2 and add it to row 1, and then make that my new row 1. So if I do one more um, operation, right? So if let me go back to white. So if I do row 2 added to row 1, that produces this one. So let me write row 2 because that's not going to change anymore. Right, so we got that, and then now taking this and adding it to this, I'll still have a 1 there. The positive 1 added to that negative 1 makes it 0, and then the negative 1 added to this positive 3 makes it a 2, and then again 0 plus 0 is 0, right? This is now an RREF, right? There we go. So let's take a look. So it in fact we could have done this in either of these two forms. Once we have it in the echelon form, any echelon form, we can identify that again, since we only have 2 equations but 3 unknowns, and now we've reduced it and we have no contradictions. What we can say is, so basically these 3 facts, or these 2 facts go together. So we have an RREF plus, we have 3 variables, so 3 variables, and 2 equations. All those ingredients, what do they tell me? They tell me that I have free variables, at least 1. Right? How many free variables? Well, it's the number of variables minus the number of equations. So 3 minus 2. So we have 1 free variable here. Which one is free? Well, if we think about it, our pivots, so our leading one, so let me circle them. These are not free. So that means, you notice x3, we never had a pivot in the 3rd column. There's no pivot in the 3rd column in this augmented system. What that tells me is that x3 is our free variable, right? So I'll just write it, I'll just say here. So no pivot in this column. Oh, that's alright, so no pivot in column 3 implies that x3 is the free variable, right? So if you notice the progression in which we've done things, that the systematic way in which we define a leading variable or a pivot, the systematic way in which we reduce the system to like this kind of simpler form, then it gives us a systematic way of identifying which variables are free, right? So now let's write down our parametric solution set. So let's do that. And in that case, okay, so the first equation says that 1x1 plus 2x3 is equal to 0. Again, that homogeneous form. And then the second equation tells me that x2 minus x3 is equal to 0. So if we let x3 be our free variable, we can use t or s. I'll go ahead and use t. Then what do we have for x2? So x2 minus t is equal to 0. So therefore x2 also has to be equal to t. So we get that from our second equation. And then the first equation tells us that x1 plus 2t has to be equal to 0. So x1 is negative 2t. So putting it all together, here is our parametric solution set written as an ordered triple. So x1 is negative 2t, x2 is equal to t, x3 is equal to t, and we know that t can be any real number. And notice, so again, note, if t is equal to 0, we do get the trivial solution, right? It gives us 0, 0, 0, which is what we expect. We expect, not just that we expect, but it is a fact. In fact, I'll state it as a theorem here to kind of wrap this up. But the trivial solution must always be one of the elements of the solution set of a homogeneous system, linear system, right? So let's go ahead and write, and I'll state this as a theorem. It is a theorem, and it basically states, and so every homogeneous system is consistent, right? And again, that's just by definition and by observing the fact that the trivial solution is always a solution. Now, what happens is, if you have more variables than equations in a homogeneous system, then it has to have infinitely many solutions, right? So moreover, if there are more variables or unknowns, so more variables than equations, right? The homogeneous system, now again, this only is true for homogeneous systems, so the homogeneous system has infinitely many solutions. This only works for homogeneous. Let me end by giving you an example of a non-homogeneous system that has more variables than equations but has no solution at all, right? So here's just so if you consider this system like x1 plus x2 plus x3 is equal to 0, and then x1 plus x2 plus x3 is equal to 1. Just by looking at the way I've set this up, hopefully a very obvious way, you see you can see this makes it non-homogeneous, right? Because we have a non-zero constant here. So this tells me that it's a non-homogeneous system. And if you think of it, there is no ordered triple that I could use to satisfy the first equation that would also satisfy the second equation, right? In fact, if you missed that, and let's say you just went through the routine of either Gaussian elimination or Gauss-Jordan elimination, either one. But let's say you set up this would be the corresponding augmented system. If I did negative R1 plus R2, right, using this as my pivot, that would produce this augmented system where I have all the ones on this side would be canceled out, but then I would have a negative 0 plus 1. I would still have a 1 there. And this is my contradiction, because this would be the left-hand side of the equation, which would be 0, and the bar there represents the equal sign, and then on the right-hand side I would have a 1. So this is my contradiction. And once your system has a contradiction, then we have no solution, right? So basically, this example here is done to show that simply having more variables than equations, it doesn't mean that you automatically, or you're going to have infinitely many solutions, right? In this case, because the system is non-homogeneous, I was able to give you the simple example to show that when you try to reduce it, you end up with a contradiction, right? But once you're working with homogeneous systems, this cannot happen. If you think about it, once I start with zeros in my very last column, no matter what elementary row operations I do, I will never change those zeros into something that's non-zero. Hence this theorem, right? So homogeneous systems, make sure you're clear on how they are defined and this very key property that's stated in this theorem. All right, see you soon.